everyone. Welcome to the channel. I don't know what the channel name is gonna be, but it will be something when I upload something. Okay, so I will be teaching you topics that I know and which I understand, and I want to help others. So yeah, that's what the channel is gonna be. I'll try reducing the music. So with that background, yeah, should be better. So today we'll start with something interesting. So let me write up. Yeah, we'll work with DSA. Because I want to teach the data structures and algorithms over here. And first, we will start with linked list. So one might ask, what is the purpose for a linked list, right? So let's explain the purpose of a linked list. Let's take an array which was supposed to be given by a user. When you give an array defined with some size, let's say 10, and if you if we resize, we will have to increase this with some new size, right? Total length would be 10 plus n, which is the variable. But for this to happen, if let's say our memory is continuous like this, right? We need our memory chunks to be free. Let's say our array was stored over here, the 10 length, and these arrays are, these next memory blocks are filled. So the extension or the resize would never be possible, right? So what our code will do, once the 10 is not like it can't be resized, it has to find the next 10 plus n length size of data blocks that has to be free in our data lane, whatever you call it, you want it, and then assign that to our new variable. And this will be slow and tedious and more of effort, right? Like copying this data to the new location and a lot of hard work. Now what our linked list does is we take a small chunk, right? And we define it as let's say this. If these were a home, right? If this was a home, right? And this home addresses to the next home over here. That would be useful. And let's say over here Ross lives. And then here Rachel lives. Right. Now what we can do is create a structure such that it tells Ross is a neighbor to Rachel, right? And then Ross stores something. Let's say Ross has a variable like uh, let's give it an integer for just to understand. So it has an integer. Ross has an integer of 0, right? And then we know he is connected to Rachel, right? The next node will be Rachel, exactly. And let's say Rachel is connected to Joey, and then Rachel has an int value, let's say 21. Now we go to Joey, right? And then Joey is connected to Chandler, obviously. And then he has an int value that's supposed to be 23. Now we know Chandler is connected to Monica, right? And then it goes to int value, whatever it can be, some random variable assigned over here, random. Okay. Once this is done, we can see that Ross, R stands for Ross is connected to Rachel, let's just put Reg, and then she's connected to Joey, J, and he's connected to Chandler, and he's connected to Monica. You see this kind of an array or a linked list, right? How it is related to one, other, and other, and other. And this list is easier because we can map out the next. Like for suppose Rachel is there and she's connected to Joey. But what if I want to say she's connected to Monica? And that's totally possible just by pointer operations, and that allows us to manipulate our list and handle it easily. And it also happens in way less time and a continuous memory. Let's say if this memory was given like this, right? If this was a normal classical array, and if I want to say I want to take this first two chunk and add this two chunk and remove this middle two chunk, it will be tough. it has to copy this and this to a new memory address, and then it has to create a an array of size 4. But what happens over here is, when we take a linked list, it connects to this, connect it, connect it, connect it, and connect it. Let's say I want to remove this node, or okay, let's take this. I want to remove this too, right? I can just take this connection, manipulate it, and connect over here, and this connection is gone, and this connection goes away, right? Then we have removed this two efficiently, such that we don't have to create a new space in a new memory allocation in our storage, and it's good for that reason. And linked list is also faster to allocate a new memory, because we know the previous address, right? When we iterate, we know Monica was the last person we know of our list, and then when we have to add, we just add something over here, and that is just O of one. But then searching an element in a linked list is slower than searching an element in our array. In our array, it is O of 1, but in our linked list, it's O of n. Because we have to iterate through all the pointers one by one, one by one, one by one, and then get to the location we have to. Imagining this as like a house, like we go from one house to the other house to the other, is easier. And that's how we take this into our conditional use case, that this linked list is better for our memory. And this can also be extended where our linked list is bidirectional like this, and this will become a doubly linked list where one node is also backward connected, so we can go from here to here and here to here. That's how it is. Yeah, I mean, there are a lot of applications for linked list, and this is how a linked list is made and used. I would suggest that. What else am I missing? Let's see what a linked list can do. Let's write a simple code. If we use C++ or C, doesn't matter. This struct, that's a linked list. It will have the integer value, what it has to store, right? And then it has a pointer. We just put it as a pointer to the next node. Don't mind my syntax, this is totally wrong according to the C++ or a C. I'm just giving a feel over here, and just this, how it is supposed to work. And then we can define add function, which takes the head pointer to our linked list, right? And then adds the new value. You can do the add operation in O of 1, or it will take O of n, but depends how you write the struct class, right? Imagine if you have a class, if it was a class, right? If it was a class, you can have your private variable over here, which says the pointer last variable. Okay. So when this happens, you can put the last pointer that it was there, and when you do an add function, it just adds a new node to this last, and then it saves this pointer into this last, and this would become O of 1 instead of iterating over there. And yeah, that's the thing. And you can save the pointer to the head over here, pointer head, and then create a vector. You don't have to create a vector actually. Oh, that sucks. Okay, now we come into this place of system design where I'm making the point where we can do it. Well, we can do up an add operation where it will take an O of n over here, but I am telling it to be of an O of 1, which will be possible when we know the previous pointer. We have to store, but if we do a add operation at given position, this will be O of n, because it will take this list, right? Let's say over here, it has to manipulate this and then take this, and then it has to cut this point. So it has to move over here. This is an O of n process. I mean O of n, where the n is the given position. I mean, it's a big process. Addition and subtraction would take in that sense, but then removing the last and the first nodes are supposed to be O of 1. Well, yeah, let's design it together and see how we can do it. Let's say if it was an in over here, and then we say the user wants to create a linked list pointer head is equals to null pointer, and then head dot next would be equals to the node with the value and null pointer. If this would become that, and then head would equal to head dot next over here, and then this points to this new node over here, and in the head dot next will be a null pointer because we stored that and the head value. So according to that, we have done an add operation over here. This is how an add operation should work. Add operation. How an add operation would be. You can just use our add operation. Okay. I get it what it's supposed to be. Our add operator would be just a simple pointer manipulation where it just takes this to this and this to this, adds over here, and then the new pointer points over here. We move the pointer from here to here, so that's how it should be. So this is how our add function is supposed to be. But if we do a add position, right? Now add a position would be a different add a position to a function add, right? And the head pointer, the main head pointer, the start of the node, that this is the head, right? This is the head, this head pointer, and the index and the value. When we do a while loop, while head pointer not equals to null. Just a safety check, okay? We do this condition is where we do head is equals to head dot next, and in the condition we do till the idx minus. So we move the head to I index. Let's just remove it to idx 2, and then we reach to this point, and this would be the next node, but we have to add a node, so this connection would be created, and this connection would be removed, and this connection would be completed, right? So once that is done, when the loop is done, we do head we create a temp variable which stores the pointer to the head dot next, right? Head dot next. After head dot next is done, we take the head dot next and then we give it to the new node which we can create with the value and this given temp. we return. If it is a void, we return void. So this is empty and this is closed. And this over here at the element at the n ith index, and then this over here joins the rest of the pointers, like as shown in the above over here. This would happen. I believe I have done the most part over here. And I'm sorry for the inconvenience because I'm teaching you guys and I'm not perfect. So please don't mind that. And if you understood it, I'd be great. And if you have any doubt, please ask me so that I bust my head open to explain it to you guys and see how it works. Love you. Bye.